So welcome everybody. Pleased to introduce Julian Burrill, who's a staff scientist at Lawrence Berkeley National Lab, who's going to talk about all the science that goes into analyzing cosmic microwave background radiation. You may remember that George Smoot won the Nobel Prize back in 2006 at LBL for the work in doing one of the first big analyses of this to figure out the structure of the universe. And that enormous calculation you could probably do on your laptop today. So the data sets have gotten a lot bigger, and we'll hear just about how much bigger.
Thank you very much. So I'm going to talk about the work I've been doing for almost 15 years now on a number of experiments. So I particularly wanted to call out Boomerang and Maxima, which were the suborbital experiments, balloons that I started on, the Planck experiment, which for the longest time, the answer to the question, when will Planck launch, was in 7 years, whenever you ask the question. But we did finally launch in 2009 and presented first results just a couple of months ago. And the EBEX and Polar Bear experiments, which are ongoing, a balloon experiment EBEX and a ground-based experiment Polar Bear. So I want to quickly give an overview of the context that this is all happening in, the history, a brief history of cosmology. It's a relatively young science, only 100 years or so old. Talk a bit about CMB physics and how we make observations of the CMB, and then focus on the high-performance computing aspects of analyzing CMB datasets. Just to give you a warning, you will see many times in the history of cosmology, and as I say, it's a very young history, that we make complete volte-fasses. And that's because we believe in the method, not in any one particular result, for the most part. So as with so many things in physics, a lot of it starts with this man. The equations of general relativity are beautiful tour de force, mathematical tour de force, but basically, on the one side of the equation, you have features about space, and on the other side of the equation, you have matter and energy. And this is the field equations of general relativity in their most concise and elegant form. Einstein came up with this and then looked at it and realized that it implied that the universe was dynamic. And everybody knew that the universe was static, so that couldn't possibly be the case. So he added this term at the end. Actually, he put it on the other side, but for reasons that will become apparent, I've chosen to put it on the right-hand side of this equation. So he introduced this lambda term, the cosmological constant, coupled it to the gravitational stress energy tensor, even though that equation, while it does have a static solution, that solution is unstable. So any tiny perturbation away from that solution would escalate off. So it was extraordinarily fine-tuned in the sense that you had to have an exquisitely precise value of lambda, and it was unstable. But even despite the ugliness of that, he considered that less ugly than a dynamic universe. So of course, the next thing that happens is that we discover that the universe is dynamic. And Edwin Hubble is working on the biggest telescope available, the 100-inch Mount Wilson telescope. So that's a 2.5-meter telescope. So if you think now we're talking about 100-meter telescopes in the offing, and 30-meter telescopes are sort of the state of the art. Telescope size, well, obviously it goes as a square of the radius, but it certainly doesn't grow anything like Moore's law. A much slower rate of growth there. But Hubble was measuring distant galaxies, although at the time it wasn't clear whether they were separate objects or things within our galaxy. And he would look at the velocity of these what we now know to be galaxies via their redshifts. So you see how a known spectral line is shifted, and that tells you its velocity, the velocity of the source, and the distance using the relation on Cepheid variable stars, which have a particular absolute luminosity to period relationship. So they're variable stars, their absolute brightness is determined from their period. If you know the absolute brightness of an object and you know the apparent brightness of the object, you know how far away it is. So he looked at these and he plotted this out for a whole range of these galaxies and discovered a linear relationship. That the velocity was proportional to the distance. The further away you were, the faster you were moving away. And the value of the Hubble constant, as it became known, was somewhere between 50 and 100 kilometers per second per megaparsec. So for every megaparsec you went away in distance, your velocity of recession increased by somewhere between 50 and 100 kilometers per second. Now this gets into one of the places where the scientific method and the rationalism breaks down a little bit. This was not a nice bell curve distribution of measurements. Is polarized into two camps, those who believed in 50 and those who believed in 100, and ne'er the twain shall meet. The value from the Planck experiment that we've just determined, the most precise measurement ever, is 67. So now we have an expanding space. Who knew? And Einstein could have predicted it. And so he calls this his biggest blunder. And it's kind of amazing to think that even someone of the mental capacity of Einstein couldn't get past the assumption that the universe was static when he could have predicted this completely, at the time, counterintuitive result simply from the mathematics of general relativity. Yes. So now we have a situation pretty much between the 30s and the 60s where we say, okay, well, I have an expanding universe. What does that mean about the beginning of the universe? What does that mean about the end of the universe? And again, things polarize into two bitterly opposed camps. No one's got any ego involved in this in any way whatsoever. So the steady state theorists, Fred Hoyle, Bondi, and co., proposed actually a very elegant mathematical construct, which we'll come back to later, that as space expands, new matter is created to fill the empty space. So the density of the universe stays constant, even though it's expanding, and the universe has no beginning and no end. It just is. Always has been, always will be. It's identical. The expansion is just filled by the creation field, C field, as he called it. And it's a very elegant solution. The alternative is if you just think about running the expansion back in time and you don't do anything like put in a creation field, well, the universe gets smaller and denser and compacts and compacts and compacts, and suddenly you've got to a beginning. And in fact, Hoyle himself was the one who coined the phrase Big Bang, intending it to be a somewhat pejorative term, but it instead got jumped on and is now the name of the theory. So now we say that everything, space, time, matter, and energy, is created in some event that we don't really understand. But it's obviously explosive. It obviously pushes to the very limits of physics, and as such is an extraordinary playground for investigating physics at the very highest energies. The Big Bang is our best particle accelerator. And that after the Big Bang, we have this expanding, cooling, rarefying universe. So the universe is changing over time. And it's one of the consequences of that, if you start from an arbitrarily hot Big Bang and you expand and cool, then there will come a time when you cool through the ionization temperature of hydrogen. So before that time, you've got this plasma. If you go back even further, and before that, you don't even have atoms. So you can, but forget all of that part. Get up to the ionization temperature of hydrogen. It's about 3,000 Kelvin. Once you drop below that temperature, the protons and the electrons combine. You've got neutral hydrogen, and suddenly there's nothing for the photons to bounce off. So in this figure here, we're sitting at the center of the figure. I'm not violating Copernicus, it's just the most convenient place to put us. This is true for any observer anywhere in the universe. As you look out in space, you look back in time. So here's my observer looking back in time, back in time, back in time, out in space, further and further and further. Eventually they hit the point back out far enough in distance that you're far enough in time that you hit the epoch when the universe was about 3,000 Kelvin. Any further back than that, this mouse does not like. Any further back than that, and you're in the ionized medium, and the photons are bouncing off free electrons, and so you have these zigzag paths. The mean free path is very short. It's the same reason you can't see into a fog. You can see to the edge of the fog, but any further in, the water droplets are scattering the photons. So we have this this image of the universe, the photons have a very short mean free path in this ionized region. We hit this epoch, what we call the last scattering surface, after which they just free stream to us, almost unaffected until today. So Alpha, Herman, and Gamov predicted this just based on the idea of a Big Bang at various points in the mid-40s, mid to late 40s, and predicted, and depending on the particular value of the Hubble constant that they chose, depending on the most recent measurement, they got temperatures for this photon field of between 5 and 50 Kelvin. So this is the cosmic microwave background. It's cosmic. It's filling all of space uniformly. Wherever you are in space, wherever you look in space, you will see the cosmic microwave background. It's microwave because it's been redshifted by the expansion. Started out as a 3,000 Kelvin field. It's been stretched. The wavelength of the light's been stretched by the expansion. It's now down to what we know to be about 3 Kelvin. And it's background because these are the primordial photons. So most astronomers and astrophysicists are looking at luminous objects, which are basically stars, galaxies. You're looking at the light-emitting things within the galaxies, quasars, gamma-ray bursters, all of these things that are generating photons through some nuclear process. Whereas we're looking at the primordial photons, the photons that were created in the Big Bang. So one of the analogies I like to use is that while the rest of astronomy looks at the furniture, we're looking for the wallpaper. So these are the photons from behind all sources, and that has some very interesting consequences for us in the sense that these photons were created in the Big Bang so that everything that has happened in the entire history of the universe has had its impact on these photons. If we can untangle that, we have a record of the entire history of the universe. So we come to the 60s. No one's really paid much attention to these predictions of a temperature because at the time that was considered, I mean, that's an absurd temperature to measure. How can you measure 5 Kelvin? So for completely other reasons, Penzias and Wilson have this wonderful radio telescope at Bell Labs, and they're trying to look for weak radio sources in the galaxy. It's the beginning of radio astronomy. So the first thing you want to do is zero your telescope, get the baseline. So you cryogenically cool it because you're looking for these faint sources, and you take account of all the human sources of radio fields, radio signals. And whatever they did, Penzias and Wilson couldn't get rid of this low-level background hum. They determined that it was not only a low-level signal, but it was coming from everywhere in the sky, and it was present at all times of day and night. So it wasn't, everything they thought of, they couldn't figure out a way that it could be anything from a terrestrial source. It was direction independent, it was time independent. They worked very hard on the instrument, as I say, cryogenically cooling it, trying to figure out whether there was anything in there. They couldn't get rid of that. It wasn't even what they euphemistically called a white dielectric substance left in the telescope horn by the pigeons that were nesting there. They sent a graduate student in to scrub that out. And no, it wasn't that. Meanwhile, down the road in Princeton, Dickie Peebles, Roland Wilkinson were actually designing and attempting to build exactly this instrument to detect the microwave background. So a mutual friend put them in touch with each other, and famously, Dickie was on the phone with these guys and heard what they detected and turned around to his collaborators in the room and said, "Boys, we've been scooped." Penzias and Wilson get the Nobel Prize for their completely accidental detection of what they thought was pigeon poop for a while, and Dickie Peebles, Roland Wilkinson get to lick their wounds. But finally it's been detected, and in fact this is the death knell of the steady state theory. In fact, slightly earlier than this, in the early 50s, Pope Pius had declared that the Big Bang was the correct theory rather than the steady state. That didn't get past referees. Fiat lux notwithstanding. So then we move on, and after the detection of the microwave background per se, there were lots and lots of efforts made trying to detect any variations in it. There had to be variations in it. where were they? And so these incredibly sensitive, more and more sensitive detectors are built and fielded, and data are gathered and analyzed, and no one can find any variation in the microwave background above 1 part in 100,000. That's not strictly true. There is one variation. There's a dipole because of the peculiar motion of our galaxy through the universe. So the direction our galaxy is moving in our supercluster, you see a slight reddening, blue shift in the direction we're moving in, so the microwave background gets a little bit hotter in the direction we're moving in and a little bit colder in the direction we're coming from. But that's just because of our peculiar motion. If you take that part out, then it's absolutely uniform. No one could see any variation in it on any scales, down, as I say, to this 1 part in 100,000. And this is a big problem, because in a Big Bang model, the universe has a finite age. And the universe has a finite age, and the speed of light is finite. It means that when you get back to the very early universe, the causal horizon, the distance between which points can have had any causal contact, is very small. So in the first second, anything that's more than a light second apart has no knowledge of anything of the other. So that turns out that if you look at the last scattering surface, it means that any points more than about a degree apart on the last scattering surface can have no causal knowledge of each other. Are out of causal contact at the time those photons are last scattered. And yet they have the same temperature to 1 part in 100,000 or better. This is a big problem. And so this is called the horizon problem. And Alan Guth was one of the first to propose a method. Many others filled in details afterwards. And he proposed a mechanism where you have an exponential expansion in the very early universe. So here's a typical inflation graph. Note the time here is going from 10 to the minus 45 seconds to about 10 to the 17 seconds today. So sometime around 10 to the minus 35 seconds, we have a period of inflation where the universe, and this is the radius of the observable universe, is going from the 10 to the minus 60 or so, 10 to the minus 40 at the beginning of inflation, and you get about 40 orders of magnitude expansion in the observable volume size of the observable universe. And then it just carries on expanding in this normal way. So this epoch here allows the entire visible universe today to have come from a single causal volume from very early in the universe. So if everything is nicely thermalized in here, then this whole region can have the same temperature today. There were a number of other problems that were solved by inflation too. For example, the flatness problem. The universe was observably very close to flat, and evolution only drives you away from flatness. By flatness, I mean that the overall geometry of space-time is Euclidean. There's no requirement for the universe to exhibit Euclidean geometry. And if it's slightly open or slightly closed at the beginning of the universe, you'll tend to get more and more open or more and more closed. So if you're close to flat today, you had to be even closer to flatness as you went back in time. So either you had an absolutely flat universe, or you had to have what we think of as another fine-tuning problem, where you have to have extremely precisely tuned numbers, which feel very uncomfortable. So that was one of the problems this solved, again, by this massive period of inflation drove everything to flatness. Another example was the monopole problem. We know from quantum field theory that we expect there to be a number of quantum phase transitions in the early universe, and these will typically leave topological defects. An example of these defects is magnetic monopoles, so single at the north or south poles. No one was seeing these. In the numbers that they were predicted, we should be seeing huge amounts of magnetic monopoles. Clearly, we're not seeing those. Again, the epoch of inflation, the period of inflation, deals with that by taking a very small volume, which will have very few monopoles in it, and expanding it to the entire visible universe. It's much easier to explain a visible universe in which you might expect one monopole. If you haven't seen one monopole in the universe, well, it's a big universe. If you're supposed to be seeing one every square meter, cubic meter, then it's a little more embarrassing. So now we have a period of inflation. And finally, in 1992, we have the first detection of these fluctuations in the CMB. Well, they have to be there. For structure to exist today, there had to be seeds of that structure in the very early universe for gravity to evolve and build into the galaxies and clusters of galaxies that we see today. So we knew that there had to be the imprint of these fluctuations in the microwave background, and yet no one was finding them. And so finally, in 92, the COBE satellite was launched to measure two particular things. It was detecting any variation in the microwave background on large angular scales. So the COBE satellite, the beams were about 10 degrees. So anything on less than 10 degree scales was completely washed out. But on larger than 10 degree scales, COBE finally saw fluctuations. COBE also measured the spectrum of the microwave background, so how its intensity varied with temperature, and by comparing it with a standard reference black body, determined that the CMB was indeed the most perfect black body in nature. There's an extraordinary plot, which unfortunately I don't have here, but that shows the spectrum measured by COBE, and they have 1,000 sigma error bars that are invisible to the eye. The measurements are exquisitely precise. So this got John Mather, who was the PI of the black body spectrum experiment, FIRAS, and George Smoot from up the hill at Berkeley Lab, who was the PI of the DMR, measuring the temperature variations, the 2006 Nobel Prize. So now the question was, well, what's the fate of the universe? So in a Big Bang theory, the fate and the geometry were considered to be intimately related, and all depends on how much matter you have in the universe. So there's some critical amount of matter. So if you imagine you've got this explosive Big Bang initial event that's driving everything apart, and then you've got a universe full of matter, and gravity is going to pull it back together. So there's a critical amount of matter that we reference, the critical density. So if we have less than that amount of matter, we talk about densities rather than the amount of matter, because the universe might be infinite, so it's easier to think about a mass per unit volume ratio than a total mass. But if you have too little matter, there's not enough to slow the expansion down. The expansion will just continue forever. The universe will get more and more rarefied. The universe is, in that case, is open. If you have exactly the critical density, the universe is flat, and after infinite time comes to rest. So the expansion slows down and slows down and slows down and slows down and asymptotes to zero at infinity. And if you have more than the critical density, then the explosion happens, but there's enough matter to slow it down and eventually stop it and turn it round, and you come back to a big crunch. So this was everyone knew this. This was obvious. And in order to measure the amount of matter in the universe, some clever folks realized that they could look at supernovae, in particular type 1a supernovae, which are what we call standard candles, things whose absolute brightness we understand. And again, we come to this thing, if you know the absolute brightness and you know the apparent brightness, you can measure distance. And these are scattered through the universe, so we can use these as kind of markers at different times and different distances, and so use the variation in their brightness and distance to sort of trace how the space between them is moving, and use that as a way of measuring the dynamical history of the universe. And so a couple of groups did this. The High Z Supernovae Search and the Supernovae Cosmology Project, and their points are on this plot in red and yellow. And so the line everyone was expecting was this red line, the critical density, and what we get is this black line here. And much to everyone's chagrin, not only is the universe not decelerating, not only are we not measuring the standard expectation, but we're measuring an accelerating universe. So everyone knew it was decelerating. The question was just by how much? Well, actually, no, it's not. It's accelerating. How can that possibly be? Well, we come back to the cosmological constant. Turns out that if you flip the sign of the cosmological constant, you can drive the expansion. So now we have a field with negative pressure that pushes space apart. No idea what it is. Doesn't fit anywhere in our standard model of high-energy theoretical physics. It has to fit somewhere. Hopefully this is a clue as to how we go beyond the current standard model of particle physics, which we know is while it's extraordinarily accurate and predictive and powerful for 3 of the 4 forces, it's completely incompatible with gravity. So we know that there are these tensions in our models. The hope is that we're in a similar epoch to the turn of the 19th to the 20th century, when the first hints of quantum mechanics, of the kind of observational evidence for funny things going on at a quantum level were coming out, and no one quite understood what they were, but they were the seeds of the explosion into quantum field theory. So we're beginning to get the hints of places, observations of things that don't fit our standard models that we can quantify, we can parameterize, but we'd really like to be able to explain. Anyhow, so for discovering the acceleration, Saul Perlmutter, the leader of the Supernova Cosmology Project, also at Berkeley Lab, and Rees and Schmidt, the leaders of the High-Z supernova search, shared the 2011 Nobel Prize. Interesting feature of the Nobel Prize, you have to be alive, and no more than 3 people can get it, but it doesn't have to be divided into thirds. So Saul, as the leader of one of the 2 teams, got half the prize, and Rees and Schmidt got a quarter each. This has a significant effect on the amount of money you get, but more seriously, the number of tickets you get to the Nobel Ball. And apparently this was the subject of some heated debate amongst the 3. So the supernovae measured the dynamics of the universe. Meanwhile, we were continuing to measure the geometry of the universe with next generation CMB experiments, and in particular the Boomerang and the Maxima balloon experiments. Maxima flying in North America, Boomerang flying around Antarctica, measured the small scale fluctuations. So if you want to look at the fluctuations on the largest scale, you need to cover the entire sky. You pretty much need a satellite. But if you just want to see the fluctuations on a smaller scale, you can look at just a patch of the sky and hope that, treat that as a representative patch and do your statistics carefully. Turns out that because of the different physics involved, the microwave background measures the geometry, so that's the sum of the dark energy, this lambda term, the cosmological constant. So omega is the fraction of this critical density. Omega equals 1 would be critical density. So the fraction of that that's in a cosmological constant is omega lambda. The fraction of that that's in matter of all sorts is omega matter. The sum of those 2 gives you the total amount of mass energy in the universe. That gives you the geometry. On the other hand, we know that the cosmological constant, the lambda term, is pushing, and the matter term is pulling. So the difference between those 2 gives you the dynamics. So if you look at either of those separately, you've got a degeneracy. We know that omega lambda plus omega matter is 1. That's the Boomerang results here on this omega matter, omega lambda plane. We know that the difference between omega matter and omega lambda is about 0.45. That's the supernovae, the original supernovae results, this ellipse here. But if you combine the 2, then you break the degeneracy, and we're locked into some region here. And it turns out that this gave us what we now call the concordance cosmology, 70% dark energy. We know that it has negative pressure. We have no idea what it is. 25% dark matter. We know that it gravitates. We detect its presence from its gravitational impact on the very largest scales, galaxy rotation curves, formation of structure in the universe. No idea what it is. 5% baryons. We know what they are. So we have quantified our ignorance at the 95% level.
So baryons being neutrons and protons and the things we see.
Baryons being the things we think of as normal matter, yeah. All the regular stuff. There are photons in there as well, but we're so dominated by the baryons are the only significant contribution from the normal stuff. So this is an extraordinary universe. It's one that no one was expecting, but it's one that pretty much overnight everyone flipped. And again, this is because our faith is in the method, not in any one particular result. So we now have this extraordinary universe where 95% of it we have no idea what it is, and we have no idea why it is. So a very interesting time to be a cosmologist. And again, hopefully these two are hints of how we expand the models of all of physics. Again, using the universe as the ultimate particle accelerator. So here's our version, our understanding of the universe. We have some Big Bang event, don't really know what that means. We have a period of very, very fast expansion, inflation. During that period, quantum fluctuations get pulled into the macroscopic scale and seed. So these are the seed perturbations for the growth of structure in the rest of the universe. And they leave their imprint in this cosmic microwave background image about 380,000 years after the Big Bang. After that, the photons free stream, essentially unimpeded, from last scattering to some satellite detector, where they finally splat against our detectors 13.8 billion years later. In the meanwhile, these density perturbations are growing and growing and growing, and finally they grow to be big enough to collapse matter to a point where nuclear fusion can start, and we start getting luminous objects. So we get the first stars, about 400 million years after the Big Bang, and a whole period of structure formation, the development of galaxies, clusters of galaxies, the key role of the dark matter in this whole period. And then finally, and very recently, we go from a matter-dominated universe to a dark energy-dominated universe. And now the dynamics go from decelerating to accelerating. So this begs as many questions as it answers. This is our current model of the universe. But again, remember the caveat, often in error, never in doubt. So the CMB is a fascinating field because, a field of photons, because as I say, these are the primordial photons. So they trace the entire history of the universe. They've been there. And so to the extent that anything has happened, it's left its imprint on them, and we can hope to unravel that. So we think of the anisotropies in a couple of ways. These fluctuations in the temperature, and now increasingly we're searching for fluctuations in the polarization of the microwave background. So these come with primary anisotropies, the anisotropies that were in the field at last scattering, 380,000 years after the Big Bang. These encode all of fundamental physics. These encode the fundamental parameters of cosmology, how the universe came to be, how you seed the fluctuations, everything that happened up to 380,000 years, including the possibility of gravity waves generated in this period of exponential expansion that will leave their imprint on what we call the B-mode polarization signal. I'm going to come on to this later, but this is currently the holy grail for CMB scientists. That will be the third Nobel Prize. Well, I used to say sometime in the 2030s, but the way budgets are going, it's probably the 2040s. Increasingly, though, we've realized that although I said that the photons free stream to us essentially unimpeded between last scattering and today, it's not exactly unimpeded. And in fact, we're now getting to a level of precision where we can use those photons as a background signal to then trace everything that happens between last scattering and us today. So we can measure the amount of gravitational lensing. That tells us about the distribution of all the dark matter in the universe. And in fact, Planck has just released the first map of the entire dark matter field of the universe, of the observable universe. It's an extraordinary thing to think about. We've just measured all of the matter in the universe. The photons can pass through regions with hot gas, and they can get upshifted by scattering off hot ionized gas. They can also pass through evolving potential wells if you have something that's undergoing gravitational collapse. The photon falls into a potential well where the gravity's collapse is happening, and then it climbs out the other side. But because the potential well is changing, the well it falls into is shallower than the well it climbs out of, and so that gives a redshift too. So we can use the very uniformity of the background field to measure all these perturbations between last scattering and today. So we can trace the early history, the fundamentals, and the late history, the dynamics, the really complicated stuff. And that's a very useful split. And essentially the split there is between the regions in which gravity can be treated as in linear theory, as an approximation, which is easy to calculate, and the regions where gravity becomes nonlinear and calculations get much harder. And so you split those two out, and we can trace both of those separately, but the calculations to try and figure out what the imprint on the CMB would be are very different. So now the challenges are twofold. Firstly, how do we detect this signal? These are 3 Kelvin photons, and we want to measure fluctuations in them of 1 part in 10 to the 6 to 1 part in 10 to the 9. So a billionth of a Kelvin fluctuation on a 3 Kelvin field. And then, for reasons that will become apparent, if you can detect it, how do you decode these physical processes from this field? So how do we detect the CMB? Well, we're looking for these micro to nano Kelvin fluctuations. So we need a lot of very sensitive, very cold detectors. Now, as I say, if we have a satellite mission, as in the top right corner here, you just go out, fly out to some suitable point in the universe and scan the sky. And in this case, this is obviously a simulation of the Planck satellite. Every 6 months, you just keep scanning, and we're sitting at the second Lagrange point. So there's the Sun, the Earth, and L2 beyond both of them. L2 is pulled around by the Sun-Earth combination. So you stay in a steady orbit around the Sun-Earth pair. You can keep your back to both of them, which is important because they're both so hot they'd fry the detectors. And every 6 months you've gone halfway round, but you're scanning the sky, so you cover the entire sky. And you end up with an image, as we'll see, somewhat like this. There's the same image in visible light, and there we are again in the microwave. Satellite missions are very expensive and don't happen very often, so we also work suborbitally and say, okay, well, if we give up on seeing the whole sky, how about we look at just a patch of the sky very deeply, and in particular we can choose patches of the sky that are free of all these foregrounds. So you see this red band across the sky here. These are all microwave signals from the galaxy. So there's an issue there. We sit in a galaxy. If we could sit out in one of the great voids, it would be much easier to observe the microwave background. Sadly, we sit in a galaxy. I guess it has its upside as well. So instead of that, we can also do these suborbital experiments. So on the bottom left here, we have the boomerang experiment launching in front of Mount Erebus in Antarctica. Here's the balloon, which when it gets up to the stratosphere, inflates to the size of a football stadium. And here is the instrument. This was the first flight of boomerang. You launch from McMurdo Station on the edge of Antarctica. You launch the balloon. 2 months of the year, there's a lovely circumpolar wind that carries your balloon all the way around Antarctica. 2 weeks later, you're back overhead and you drop the balloon down. So the first flight of boomerang, we landed about 30 kilometers from the launch site. Beautiful. Second flight of boomerang, the circumpolar wind failed while the instrument was over the Russian sector. As you know, Antarctica is divided into these superpower sectors. and had to eventually be abandoned and landed. And the only thing within 500 miles was a statue of Lenin. So that one was a little harder to recover. Took a special flight out from the South Pole to recover that payload. The third alternative is to work from the ground. The challenge with the ground is the atmosphere. So you want to go somewhere very high, and in particular, the challenge is water vapor in the atmosphere, so you want to go somewhere very dry. So the two favorite places people go are the South Pole, very high, very cold, which also helps you be very dry. Not a lot of water vapor in the air at the South Pole. That's obviously not what's in this picture. The disadvantage of the South Pole is that, so when we have a satellite mission, we get to scan the sky in whatever way we choose. When you have a suborbital mission, you're somewhat constrained by the gravity of the Earth. And in particular, when you're sitting on the Earth, it's spinning. So your scanning strategy, the way that you observe the sky, is largely dictated by the motion of the Earth. If you sit on the edge if you sit at the equator, you can see a big chunk of the sky. If you sit at the pole and you're relying on the spinning, if you sit exactly at the South Pole and look up, you see the same point in the sky all the time. So the South Pole is a very nice place in terms of the water vapor. It's not so good in terms of how much of the sky you can see. So the second favorite place is the Atacama Desert in Chile. Very, very high, very, very dry. You have to use oxygen to work on these telescopes. So mostly because you get kind of woozy and stupid when you get a little bit of oxygen deprivation. And they were discovering people were thinking they were tightening bolts but turning them the wrong way, and they could do that for a couple of hours. And everyone wears oxygen while they work on these experiments. But again, very, very high, very, very dry. So what do we measure? Well, despite the fact that we're working with these exquisitely sensitive detectors and we're gathering enormous data sets, we're completely dominated by noise. So thermal noise in the instruments. And in particular, one of the great challenges with the CMB work is that the noise is not white. So we work with some extraordinarily sensitive detectors, but they're so sensitive that if you give them a kick, it kind of rings. So the noise at some point is correlated with what happened before and has an impact on what happens afterwards. So when we come to do the analysis, we can't just do the sort of typical averaging to drive down white noise. We have to do something a little more subtle. But if we do that right, then we get maps of the microwave sky. Here are the Planck maps. And one of the joys of being able to, I've been lecturing in this class now for 7 or 8 years. Planck has been in progress all of that time, but now for the first time, I can show real Planck data. We have published results. So Planck observes in 9 different frequencies between 30 and 857 gigahertz. And so here are the temperature maps from Planck at those 9 frequencies. And you can see anything that sort of looks speckled blue and orange, we hope is the microwave background, but all this red and gray stuff is foregrounds. And so you can see that the 2 highest frequencies are completely foreground dominated. Even 353 is heavily foreground dominated. The advantage is that we can use those frequencies to clean up these frequencies. So we know that the CMB has a perfect blackbody spectrum. All the foregrounds have completely different spectra. They have power law spectra. They have a wide variety of different spectra. So by using those different spectral dependencies and having observations at multiple frequencies, we can separate out the CMB from the foregrounds and get a map like this. This is the honest-to-goodness Planck map of the microwave background. And now we can analyze this, and this is, it's a beautiful map, but it's only one realization. This is what the universe looks like to us, but if we went to a different Hubble volume, we'd be in the same universe, but we'd see a completely different CMB because it's a random realization. So we want some statistical characterization of this that encodes all of its information, and because we're looking at a signal on a sphere, the appropriate basis set are the spherical harmonics. And so we do basically a spherical harmonic transform on this, and then we assume azimuthal symmetry. So there's no dependence on the M mode of the spherical harmonics, collapse those down, and just look at the L dependence, so the dependence in the strength of the signals on angular scales, the angular power spectrum. So here's multipole. So these are large angular scales, these are small angular scales, and here's the fluctuation in temperature units in microkelvin. And we've got 4 spectra on here. So we're going to decompose we're looking at the CMB temperature, and we're decomposing its polarization by analogy with electromagnetism into an E mode and a B mode. So a gradient-free and a curl-free field. So we're looking at the spectrum. The temperature spectrum is up here. The temperature cross E mode is this one, the green one. The E cross E is the purpley one, and the B cross B is this red one down here. So these are the projections for what Planck should see. This was from way back when. And there is an extraordinary amount of physics encoded in these spectra. So for instance, the location of this peak tells you the geometry of the universe. Given where it is, it tells us that the universe is flat. The ratio of the heights of the peaks tells you the amount of baryons in the universe. So all of these different physical processes will tweak these power spectra in slightly different ways. This bump here tells you about the early reionization history of the universe. And the 2 big things we're hunting for particularly now are in this B mode spectrum, which is basically 2 bumps superimposed. The big bump here is due to gravitational lensing. So this is the dark matter between last scattering and us, lensing the E mode signal into a B mode signal. So that's not a fundamental signal, that's due to post-processing. But this bump here, this is the one that we expect to be coming from gravity waves generated during inflation. That one will give us the energy scale of inflation. It will be the sort of smoking gun that will finally nail inflation down as it must have happened, and will be, as I say, the 3rd Nobel Prize in the field. So this is sort of the ultimate goal of CMB analysis, is to produce spectra like these. These are properties of the data, and then we take a cosmological model and say, in this cosmology, what would these spectra look like, and compare the 2, and use that as a measure of the goodness of fit of a particular cosmology.
So these curves are idealized?
These are idealized curves, yes. These are projections of what Planck should see given its sensitivities. And just tying in some of the theoretical. So in particular, the height of this bump compared to this bump depends on the energy scale of inflation. And so it could be down here, yet another order of magnitude fainter. This is the most optimistic scenario. So over time, since the serendipitous first detection, since Penzias and Wilson, the science goals for the CMB have evolved. We've been trying to extract more and more science out of it, and that's required 2 things. It's required us to go to higher and higher resolution to be able to distinguish variations on smaller and smaller angular scales, and it's required us to include polarization sensitivity. So here's just a comparative plot of the 3 generations of satellite that have flown so far. So Kobe had these 10-degree beams, and just saw the very large scale fluctuations. The WMAP satellite had about half-degree beams when you combined all its channels and saw this kind of blur, and then Planck down to 5 arc-minute beams, very high resolution, and starting to include polarization, which is on as a vector field here. It's a little hard to distinguish. But you can see that we're sort of how the increase in precision affects the map that we see. And we saw that before with the image of George Smoot standing in front of the Kobe map. That was the honest-to-goodness Kobe map, just lots of big splotches. And then the Planck map, very, very high resolution, fine, fine detail. So we're looking for fainter and fainter and fainter signals. And the only way we can extract those from the data is to gather a larger data set. We're down at the noise limit of the detectors, so the only way to increase our signal to noise is to get more signal. The other challenge with going to higher and higher signal to noise is that you now have to be concerned about more and more subtle systematic effects. So the analysis gets more complex inherently, and the data volume that you're analyzing gets larger, and you deal with all the complexities due to that. So here we have a set of observations from COBE through Boomerang and WMAP and Planck into some of the next generation experiments, and ultimately the proposed CMB polarization satellite sometime post-2020 at this point. And you can see that we're going from order 10 to the 9 observations for COBE to 10 to the 15. So we went 3 orders of magnitude between COBE and Planck. We're looking for another 3 orders of magnitude between Planck and CMB pole in observations. And the pixel count, well, that depends a bit on whether you're doing an all-sky satellite mission. So COBE 10 to the 4, WMAP 10 to the 7, Planck 10 to the 9 pixels, CMB pole maybe 10 to the 10. That's covering the whole sky. Or if you're looking at partial sky where you get fewer pixels, although still large numbers. We're going to be dominated by the number of observations, and you can see that we're looking at 1,000-fold increases in the data volume over 15-year periods.
So it's the product of those two columns, it's the data set size?
No, we're actually dominated just by the number of observations at this point. I'll come on to this in more detail. So we have a data volume in terms of the number of observations that's growing with Moore's law. And it's going to grow with Moore's law over 10, it has already grown over 10 epochs of Moore's law, and it's projected to grow again for another 10 epochs. So we really need to have our algorithms scale through 10 M-foldings, 10 iterations of Moore's law, and that's a far from trivial task. So I'm going to focus on the analysis now. In principle, it's very simple. As I said, this is before nonlinear effects come in, so the physics in many ways is very, very simple. We can make simple assumptions of Gaussianity in the noise and in the CMB field, and just maximize Gaussian likelihoods. Very simple to write down, simple to perform, unfortunately complicated by reality. In particular, the colored noise, the correlated noise has to be dealt with. I should say non-ideal data, not non-deal data. So there are these foregrounds in the way. However much we beg them, the experimentalists don't make perfectly symmetric beams. There are glitches in the data. It turned out that Planck, with all its delays, ended up launching at the time of a solar minimum, which meant that the flux of cosmic rays was much higher than usual. So we have a lot of cosmic ray hits on the Planck detectors, lots of glitches in the data that have to be cleaned out. That's one side of it. And then the other side, as I said, was about we have to have algorithms and in particular implementations that will scale both with the CMB data volume and with the evolving architectures. So if we want to write down, we write down these exact solutions. They're very simple equations. But if we want an exact solution, and we want that exact solution to represent a sufficient statistic at the end, we need not only the data, but we need the correlations in the data. And this is where the challenge comes in. So in particular, if we want to make a map, we need not only the map, but we need its correlation matrix. It's a dense matrix. If you remember the numbers I was writing down for the numbers of pixels, they were going to 10 to the 6, 10 to the 7, 10 to the 8, 10 to the 9. I don't want to do NP cubed operations on billion by billion dense matrices. In fact, essentially, that whole research field and that whole area, which worked very nicely for the maximum boomerang experiments, that was the method we used, falls apart as soon as you get above order 10 to the 5 pixels. Once you start hitting the million pixel threshold, number of pixels cubed is just exorbitant. Even number of pixels squared, being able to read a matrix into memory is a problem. So we had to develop alternative approximate solutions. And in particular, we get to throw away the correlation matrix. That's where all the problem comes in. So we can solve for the map, and we can solve for the map very accurately, but instead of using the exact solution and the full correlation matrix, we can just use conjugate gradient techniques and solve for that. So it's now an iterative solution, and it just scales with the number of samples. So number of iterations times number of time samples. Once we've got the map that's come out of that, well, the issue with the map, in an ideal world, if I just gave you that perfect Planck map, And I said, this is really the universe. Great, we'll take a spherical harmonic transform. That's easy to do. But in practice, the galaxy is in the way. However well we think we can do the component separation for visual purposes, for extracting precision cosmology, that galactic plane section in the middle has to be thrown away. So now I don't have a complete covering of the sphere. I've also got bright point sources. I've got stars and galaxies and things that are polluting my map. I've got lots of holes in my map. If I try and take the spherical harmonic transform of that, the spherical harmonics are no longer a complete orthonormal basis set. So I've got this sort of ugly partial sphere. And moreover, I've got noise that's not homogeneous over that sphere. So the spherical harmonics, and it's just not an accurate representation of what's really there. But we can do that anyway. It only takes a number of pixels to the 3/2 operations to do a spherical harmonic transform. And we'll call that the pseudo-spectrum. It's not the real spectrum that we're going for, but it's the result of what happens when you take the spherical harmonic transform on this cut sky with inhomogeneous noise over it. And then we correct for that. And how do we correct for it? We correct for it with Monte Carlos. So all we have to do now is generate 10,000 realizations of our data set, put it through the same analysis chain, and use the result that comes out at the end of that to debias our results and to quantify the uncertainties in those results. So now that's going to scale as the number of realizations times the number of iterations, because this is again going to go through the map making. So we're going to simulate the data and then map it. And this suite of maps is going to be our Monte Carlo set. So it's basically number of realizations times the map making. So for Planck, this is, we're ultimately wanting 10 to the 4 realizations. Typically these calculations take about 100 iterations to converge, and we've got 10 to the 12 observations. So there's a nice 10 to the 18 flops. So here's how the analysis has evolved over time. So with the early days, with the boomerang data, the early boomerang data, we were working on a T3E, 700 core T3E. We could do the explicit matrix inversion to make the map. We could do explicit maximum likelihood with Cholesky decomposition and triangular solving for the power spectrum. The next generation data, the second boomerang flight, we're working on a 3,000 core machine, but the communication is much worse. So we can carry on doing the explicit maximum likelihood for the map, but now the communication for the Cholesky and triangular solve is too heavy, so we have to do an explicit inversion and multiplication. And then when we get up to the Planck size data, we have to abandon those methods entirely. So we're using PCG map making. We're now up to about 6,000 cores, and we're doing Monte Carlo simulations to correct and debias our pseudospectra. And in this case, the initial approach was to simulate the data and then map it. And we moved up to, this was for a single frequency of Planck, this is for all frequencies of Planck, or for things like EBEX, similar size data set, now running on about 40,000 processors. We had to couple the simulation and map making in a single code. I'll show you this in a moment. And now we're doing full Planck Monte Carlos on 150,000 cores at a time on the XE6. And this has required hybridizing the code. And so these last couple of steps are the things I want to go into some more detail about. Here are just the examples, again, going from single maps made on 128 processors to 10,000 maps made on 32,000 processors. So the first single frequency Planck realization, this was the challenge we faced. We knew that the Monte Carlo was going to be the biggest thing. So going back to 2000 when I first started working on this, we knew the Monte Carlos were going to be the big challenge. 2006, we did the first single frequency Planck simulation and map making. So it took 6 years to get to the point where we could do a single frequency. There are 9 frequencies on Planck. And that was 36,000 CPU hours for one realization. So we want to do 9 frequencies, we want to do 10,000 realizations, but we've got till 2012 to do it. So if nothing changed, we would need about 3 billion CPU hours. That's getting a little heavy. We allow for Moore's law. Well, we've got 6 years in there, so we've got a factor of 16 from Moore's law. So that takes us down to about 210 to the 8 CPU hours. 200 million CPU hours? That's sort of lattice QCD territory. Unfortunately, fortunately, the good news was that Planck had an agreement between NASA and DOE that we were guaranteed access to NERSC for the life of the mission. Unfortunately, the quota by about 2012 was never going to be more than order 10 million hours. So this meant that we knew from the outset that we were going to have to do two things. First of all, we were going to have to be able to scale through the next 4 generations of machines, through the next 4 cycles of Moore's law, even from 2006. And also that we were going to need to find an additional 20x or so speed up, either from algorithms or from their implementation. So just to see where we might improve things, so we want to simulate the data. The data is made up of noise and signal. The noise requires doing pseudo-random number generation. That has its complications. If you want to do pseudo-random number generation for 10 to the 18 or 10 to the 12 samples 10,000 times, you want 10 to the 16 pseudo-random numbers, you'd like them to be uncorrelated. So you have to do some slightly clever things just to make sure you're not having overlapping subsequences and things. And then you're going to use Fourier transforms. For the signal, we're going to use spherical harmonic transforms to convolve.
Question: how big are the FFTs?
The FFTs are band limited, so they're not particular. They're not too bad. They're all serial FFTs. We have spherical harmonic transforms to put in the signal, and then we have this. This is the exact solution of the map-making equation. The data in the pixel domain as a function of the data in the time domain. This has the AX equals B form. We solve it as a PCG. So the first thing we have to do is build the right-hand side. Turns out that we can multiply by this noise matrix without ever explicitly building the noise matrix, because the noise matrix is diagonal in the Fourier domain. So we take our time domain vector, Fourier transform it, apply the the noise matrix as a diagonal matrix. That I can do cheaply, and then project it back to the pixel domain. So that's basically an FFT and a sparse matrix vector multiply. And then solving for the map is doing conjugate gradient iterations over the same process. So you can see that we're down to pretty much FFTs, potentially a spherical harmonic transform, and sparse matrix vector multiplies. So the FFTs are pretty well optimized. We could certainly improve the sparse matrix vector multiply if we can figure out good structural decompositions. But algorithmically, there aren't huge numbers. The other place where we could hope to improve things is in the number of iterations the PCG takes. So come up with a better preconditioner. So there's certainly some room for algorithmic work. But even more, there's not only the ability, but there's a requirement to do implementation work. So obviously these, in an ideal world, everything would scale linearly with the number of observations. They're band-limited FFTs, so there's not even a log n on them. And we would be able to scale to arbitrary numbers of cores. But of course, that doesn't happen. And in particular, as we know with any massively parallel system, all the money goes into the flops. Some of the money goes into the communication, and very little money goes into the I/O. So we have this hierarchy of inefficiencies. The I/O is horrendous, the communication is painful, and the flop count is pretty good. And again, it comes down to the usual thing about delivering data to the processors fast enough to take advantage of their capabilities. So in particular, the code development, there's been this ongoing history of facing these challenges with every new system. You've got a new balance between the I/O, the communication, and the calculation, and you have to tackle that algorithmically and in particular through implementations. So here's what we used to do. For every Monte Carlo realization, we'd read in the pointing for every detector. We'd calculate where it was looking on the sky at that time. We'd draw the signal, we'd generate some noise, and we'd write out that detector time stream. Then we'd turn around and we'd read all of those detector time streams back in, make a map out of them, and write the map back out. Incredibly inefficient. It would require for Planck reading about 500 petabytes of data and writing 70 petabytes. On a massively parallel system, particularly where you've got
Is this situation with the file I/O, like, is this kind of in your calculation before the 20x speed up that you're looking for?
Yes.
So this is kind of low-hanging fruit?
Yes.
Okay.
So many things we can do. First of all, you don't need to know the pointing of every single detector, you just need to know where the telescope is pointing, and then you can figure out where each individual detector is pointing on the fly. So on-the-fly pointing reconstruction. That gives us a huge compression in the amount of pointing data that we need to read. And then the big one, rather than doing a simulation, writing the simulation out to disk, and then reading it back in to make the map, do the simulation on the fly. So we embed the simulation software inside the map-making software. When the map-making software says, go get me this data, under the hood we say, oh, does this data exist? No, better simulate it then. Do the simulation, pass that back. Avoid all the I/O. And finally, a very simple and obvious thing to do is put the Monte Carlo loop, embed it deeper in the code. So anything that's common to all Monte Carlo realizations, do once on the outside, and then Monte Carlo in a loop. So now we read just the telescope pointing. For each detector, calculate the detector pointing on the fly, and then do the Monte Carlo realizations. The pointing is common to every realization. It's only the data that differ. So now we do the simulation embedded in the map making, and then write the map out at the end. So now we only have to read the sparse pointing, and we write out number of realizations times number of pixels. So then we now read, instead of 500 petabytes, 2 gigabytes. So we have got a 10 to the 8 compression in reading and a 10 to the 3 compression in writing. This saves an enormous amount of time. The communication, so we split the data up over all the cores. Each core has some section of the time stream. Each core looks at that section of the time stream, and those are some of the observations in some of the pixels. So at the end of every PCG, we have to do a reduction to get all of the observations in all of the pixels to build the map. So what we used to do was there would be one MPI task on every core, distribute the data stream, and then do this very ugly, because it was quick, it was easy to code. So you take the little local bit of the sky that you saw, you'd pad it out with zeros to the full sky and do an all reduce. And then once you got that reduced vector, pull out the pixels that you were interested in, throw the rest away. So lots and lots of reduction done on zeros, lots of reduction done between processes that had no common pixels. So a much better way of, two things we had to do to improve this, much better way of doing this. First of all, hybridize the code. When you get to very large operation counts, 100,000 MPI tasks, it's going to kill you. So MPI only off node, use threads on the node. And the second one was to reduce the total volume by, for every pair of processes, figure out what their intersection is, and then use a scatter gather or an all-to-all V in place of the all reduce. So only communicate those things that need to be communicated. So that's what we do now. It turns out that it's a little more subtle than that. If you're looking at something like Planck, where you cover the whole sky, then the intersection between pairs of pixels is typically between pairs of processes is very small. So it's worth doing this. If you're looking at something like one of these suborbital experiments, they're looking at a small patch of the sky, and they scan the entire patch fairly quickly, and they just do it many, many, many times. So that means when you chop the data up into these intervals of time, they're pretty much all looking at exactly the same patch of sky. So in that case, the all reduce is still the optimal way of doing it. So here's the big result. So this is 3 generations of our Monte Carlo work. Here's the first run. Now, note these are log scales. So this is the number of seconds per realization. This is 6 hours in 2006 on 3,000 cores. When we went to the next generation system, we couldn't even run it at all, going up to higher concurrencies. The I/O was just completely killing us. So here's what you get when you fix the I/O. This is running on up to 32,000 cores on the Franklin system. And you can see that we do a lot better, except as we go to higher and higher concurrencies, the communication is now killing us. So then we fix the communication, and we can go up now onto Hopper, going up to 150,000 cores. And these 3 curves are different configurations of Hopper, different numbers of threads per process. And I'll talk about why that is in a moment. But in between them, we got a 250x speed up between the slowest and the fastest. We got our 16x from Moore's law, and we got 16x from the implementations. And we hit our sweet spot. Just-in-time computing. So one of the interesting things that's happened in this process is that, obviously, as I was saying, that the systems that we're working on have evolved. And in particular, for a long time, we were just seeing the clock speeds go up and up and up and up. And as I'm sure has been discussed extensively, that ain't happening no more. So here's an example with Hopper. It turns out that Hopper has 24 cores per node, but it's not really 24 uniform cores, so we're getting into this issue about heterogeneity. So it has 2 sockets per node, so there's a big distinction. Each socket has 2 NUMA nodes. So basically it's really 4 memory blocks, each with 6 processors attached. And communication with your local memory is very fast. Communication with the other memory on the same socket is slow but not impossible. But once you start going crossways, things really start hurting. We get a lot of non-uniform memory access issues. So how should you run hybrid code on such a system? So coming back to this plot, what we see is this is for a single calculation size. At low concurrency, it works best to run with the NERSC-approved 4 tasks per node, 1 on each memory block, and 6 threads per task. That's the blue curve. And the difference between the blue, the red, and the green, as we go to fewer tasks per node and more threads per task, is simply these non-uniform memory access issues. And remember, again, this is a log plot, so this is a very significant difference. However, out at the very high concurrency end, everything's flipped around. And now the fact that we have a quarter of the number of MPI tasks in the green case compared to the blue case means that the MPI cost is dominating. And so at very high concurrency, it's more efficient to take the NUMA hit, but run with fewer MPI tasks. So now we have a situation, and this is kind of a precursor, this is only going to get worse. As the heterogeneity of the systems increases, as the complexity of the systems increases, as the diversity across systems increase, these kinds of effects of the efficiency being concurrency dependent for a single job and the requirement for things like auto-tuning are going to become more and more important. So here's the big result. So this was what we were working towards. This is the 6th realization of the Planck full focal plane. So this is now the 6th time that we've simulated the entire Planck mission as the characterization of the instrument has got better, as our understanding of its performance has got better. We've done more and more realistic simulations. There are 2 things in this. On the right-hand side, you see these are simulations of what Planck would see given our best understanding of the sky. 9 frequencies, 7 of them polarized. So this is the polarization signal, this is the temperature signal. The value of this simulation is that you can apply all of your analysis algorithms to the simulated data, which has known inputs, and do validation and verification that you're getting the right answer, so that you know that your analysis codes are reliable. So that's the first thing. The second thing we did was the Monte Carlo realizations. In fact, we were only able to come up with 1,000 realizations because it turns out that the analysts wanted 10 times as many maps as they had previously suggested. So they wanted all kinds of different detector sub-combinations and splits in the data so you could do jackknife tests. So in fact, 1,000 realizations of the data ended up generating 250,000 maps. So this is by far, by 3 orders of magnitude, the largest CMB Monte Carlo set ever fielded. We know that next year and the year after, when the next 2 Planck releases come out, we're scheduled to release 2 more rounds of the data, and we're going to need to get to the 10,000 realizations. So we've got another order of magnitude to find between now and...
So the movie we were watching were different realizations?
Yes, so the movie is 10,000 realizations of the Planck noise at a single frequency. And what you can see is that the noise is very inhomogeneous. There are parts of the sky that are very quiet, here and here, and there are parts that are very noisy, in particular around here. You can also see all kinds of other things if you let your eyes sort of blur. But the reason for that is just because of the scanning strategies. Planck scans around the sky. Remember that movie at the beginning? Doing these big rings on the sky. So the poles of these rings get very, very well sampled. The poles in this case are here and here. So the poles are very well sampled, but the equatorial region is much more sparsely sampled. So this is exactly why we have to have these Monte Carlos, because this gives us all the realizations, allows us to characterize that noise in a statistically reliable way to account for that non-uniformity in the analysis. So 2013, March this year, 28 papers were released. The extraordinary thing is that there have been 28 papers generated from that initial release since then, so in the first month. And in fact, 7 papers came out by people outside of the Planck collaboration doing analyses of the Planck data within 2 days. Now, we had announced long in advance when the release was going to be, so I'm figuring there were a number of people who had papers ready to go. They just had to drop the Planck numbers in and put it out the door. So the highlights of the work, well, the data, the big highlight, of course, is getting the front cover of the New York Times. That was very gratifying, particularly since we had a DOE program manager visiting, and that always turns out to be the, what have you done for me lately? Well, I got you the front page of the New York Times. But it turns out that the Planck data are exquisitely well fit by a 6-parameter model. So we can describe all of cosmology in 6 numbers to shocking precision. I mean, it's kind of been very interesting. In my lifetime, cosmology has gone from a field where a factor of 2 was precision to a field where we're talking about sub% level effects. We've also seen, interestingly, some tension with previous results. We have 2% more dark energy, 2% less dark matter. Sorry, other way around. More dark matter, less dark energy. We're broadly within the error bars. Much more significantly, we have a 10% shift in the Hubble constant compared to the values obtained by the Hubble Key project. The Hubble telescope had a big project to measure, again, using the distance ladder, measuring things like Cepheid variables to do these distance brightness relationships. And that's in fairly significant disagreement. That's a 2.5 sigma discrepancy. So that may be telling us something interesting.
That's the 67?
Yeah.
Okay.
We have this map of all of the dark matter in the universe, at least as a line of sight density. Because of the way the physics works, we can tell you how many neutrinos there are. There are 3 light neutrino species. If there were more light neutrino species, the evolution of the universe would be different and we'd get different results. And we can cap the mass, the sum of their masses. So we've measured the sum of the masses of the neutrinos to be less than 0.23 electron volts. The particularly interesting feature, and this is still early days because it starts challenging the orthodoxy, is it looks as though there may be some asymmetry in the universe. And there are some spots on the sky that are much colder than you would expect in a normal distribution. Now, these could just be statistical outliers. The asymmetry in particular, were that to hold up, would be something very profound because it's been generally assumed that the universe is homogeneous and isotropic on large scales. So that would be a game changer. But the interesting thing for me about all of this, obviously, is that every single one of these results required these enormous simulation sets, both to validate the analysis software and to do the debiasing and the uncertainty quantification. So this is an absolutely crucial central piece to the entire analysis.
So when you say that's the sum of the masses of all the neutrinos in the universe...
So it's the sum of the masses of the 3 neutrino species. So if you took one of each species, that would be... you get to constrain what the 3 neutrinos together can weigh.
Okay.
So from here on out, well, we know that for next year and the year beyond, we need to go up by a factor of 10. Fortunately, NERSC is taking delivery of a new computer, which has a much better communications subsystem, and it looks like running our existing code. It already runs 10 times faster. Bonus. But beyond Planck, there are a number of suborbital experiments currently working that will gather data sets 10 times as big. There are a number of suborbital programs being proposed and developed now to go online in the next 2 or 3 years that will gather 100 times as much data. And of course, we're looking at a future satellite mission with 1,000 times as much data. So here's the Moore's law in the data. We've got to stay on the bleeding edge of computing just to keep up with the data volume. What is that bleeding edge going to look like? Well, it's going to start hemorrhaging. We're looking at potentially systems with 1 million cores. Now, the blue genes were the big push in that direction. That line looks as though it's being discontinued. So it's going to be very interesting to see where that goes. Certainly the alternatives look like having very heterogeneous nodes, so whether that's mics or GPUs. Portability across platforms is going to be a big challenge. And certainly as we go to the generation beyond next, the limitations in power and power-aware and power-efficient computing are going to become critical. And I'm guessing that... Did Kathy come and talk?
She speaks next on Thursday.
Excellent. This is something that is of great concern to her, amongst others. So just to conclude, I hope I've given you a sense of the way in which the CMB provides us this extraordinary view of the universe. It's a snapshot of the universe as it was at redshift of 1100. And it encodes all of the physics of the very early universe, the fundamental physics, and of the late universe in these secondary anisotropies from the nonlinear evolution of structure. But the analysis of these data sets is an extraordinarily challenging computational task. We spent about 15 million hours on FFP6 in the end. But that was as a result, as I say, of these two things, both evolving with the data volume and evolving as the HPC systems evolved. So it's a dynamic problem. It has no final solution. And funding permitting, we can see at least another 15 years of this going through another 10 rounds of Moore's law. But it's absolutely fundamental that we do this because the science we are able to extract from these data sets is going to be absolutely dependent on our computational capability and our ability to exploit it. And we've already seen this. Planck is a $1 billion satellite mission, and some of the Planck results are compromised by not having enough computing. So there's a real tension there between, if you're going to spend $1 billion on the instrument, you better have the backup to be able to exploit that data. It's way too expensive data not to get all you can out of it. Thank you.
So are there any more questions? So Julian is a local, so you can always follow up with him at LBL. Okay, thank you.